Hello everyone, welcome. I'm Swapnil Gaikwad. I work at Manchester as a compiler engineer. So, as Java developers, we know that Java code is converted into the bytecodes, and those bytecodes are executed by the JVM or Java Virtual Machine on the system. We also know that computers run instructions, assembly instruction, ones and zeros. But when I was learning about Java, I was curious, like, hey, how these bytecodes get converted into these assembly instructions. And when I tried to look up the information, I wasn't sure where to begin with. So if you are in the same position as I was, then this talk is for you. So here the idea is not to explain how compiler works end to end, which is quite a big topic in itself. But here idea is if you want to learn about compiler, want to know a bit more about it, want to see, hey, how this particular piece of Java code is optimized, then you should get enough inputs and enough directions to look into different parts of the code base. So we are going to use Graal today, and we'll see more about it. So first, we will start with a life cycle of a Java program, so how a simple program gets executed on a JVM, and how different parts of the JVM come into play and when they are invoked. So for example, you may have heard these terms like interpreter, just-in-time compiler, or a JIT compiler. So you will know how they come into play to execute your program. Then we will take a simple program and see how your interpreter executes it, then how it gets compiled, and what machine code gets generated for it. So we are going to use Graal as a compiler, and then we will tweak it a bit, and we will see how a JIT compiler optimizes your code. And this should give you enough idea and enough input so that you can take your own code, tweak it a bit, and see how the assembly is emitted for it. So I have all the slides, everything uploaded on GitHub, and there is also a Docker image which you can use to execute all the examples that I'm going to demonstrate. So, and this QR code I'll also show at the end of the talk. So let's get started. So another thing, you may see the gray box at the end of the slides. So that gray box is basically or roughly the commands that you would execute to get the output that you are going to see or relevant to what you are seeing on the slide. So we have our mytest.java file. We use Java C compiler to get the .class file, which consists of bytecodes, and we execute it using Java space mytest. So this Java or java.exe on Windows is our Java virtual machine or the JVM. So let's look into it a bit if it works. So here is our Java bytecodes given to the Java virtual machine, and Java virtual machine executes it. So first, when you execute any program, it essentially starts from the main method, and then execution of any program is like executing sequence of methods one after another. So when we look into the compiler, or when you want to understand how it works, we see in the context of a method how a particular method is executed, and that applies to how the entire program is executed. So first, when your method is called, it is given to the interpreter. So Java virtual machine says like, oh, you have called this method, let me interpret it. And then interpreter takes the bytecodes, executes it, and you see the output. When the same method gets called over and over again, then JVM says, hold on, this seems to be an important method. So let me compile it for you. Let me get the optimized version of this method so that when you want to execute it again, it will be faster. So during the execution itself, JVM sees the call to the method and compiles it on the fly. That's the reason you have the compilers that are called just-in-time compilers, because the compilation happens just in time. So what happens is, whenever a method gets called again and again, JVM puts the request for compilation to the JIT compilers, and this compilation happens in the background. So in the meantime, if you call the same method, it will be interpreted. And after some time, because compilation takes some time, the assembly for your method is ready. The method is compiled, and then JIT compiler says to JVM like, okay, here is the method. It is ready and compiled. So from that point, when you call the method again, then the compiled version of the method gets called instead of the interpreted version. So, and this is the typical approach that many JVMs or many mainline JVMs use. So there are different implementations available from Oracle, Amazon. You can see Azul have a booth there. Azul has a really good JVM. So there are many different JVMs that you would find, and they use the same approach. For today's talk, we are going to use the Hotspot JVM. And Hotspot JVM has two JIT compilers. One is called client compiler and another one is called server compiler. Client compiler is also referred to as C1 compiler. So what happens is when your method gets called again and again, first JVM gives it to the client compiler and compiles it using the client compiler and uses that version of the method. Now you are executing the version compiled by the client compiler and you keep calling it again and again. And after some point, JVM decides to compile it using server compiler. So the difference here is with the client compiler, you don't do all the optimizations because optimization takes time. And as we have discussed, until the compilation happens, we don't have the assembly. So we cannot go and execute the faster version of the method. So what client compiler does, it takes your method and it will give you some version of the code which is faster than the interpreter, but not as fast as the what server compiler can give. So it would not do certain optimizations, but it would do certain optimizations that are faster. So you will get some code which is having some intermediate speed. So what we are going to do is we are going to use Graal today. So it is the hotspot JVM, but instead of using the server compiler, we are going to use Graal compiler. So Graal is again, you may have come across Graal in different contexts. So Graal is a JIT compiler that you can use in a hotspot JVM instead of a server compiler. So, depending on how often your method is called, JVM decides to compile it using one compiler or the other. So this approach of JVM is called tiered compilation approach. So basically, depending on how often you have called the method will be compiled with either client or server compiler, or in this case, the Graal compiler. Cool. So let's look into some code, a simple Java program. So we saw mytest.java earlier. So this is the code for mytest. Pretty simple. We have our myIncrement method here, which takes integer argument, adds 1 to it and returns it. And we are calling it from the main method with argument 5. So basically it should add 1 to it, it should return value 6, and we are discarding the result. So this is our simple program. Let's see how it gets executed. So if you want to see the bytecodes that are present in the .class file, you can use java p-c and mytest.class. So you will see all the bytecodes for the entire class file. This is the sequence of bytecodes for myIncrement method. So we have 4 bytecodes: I load 0, I const 1, I add, and I return. Let's see how it gets executed when we call it using with the argument 5. So interpreter executes a program as a stack-based machine. So basically all the operations that are performed on the stack. So all the bytecodes are the instructions for this machine which performs operations on the stack. So bytecodes essentially say what type of operation you would perform on this particular stack. So first we call this myIncrement method with argument 5. We have our first bytecode iload 0. When you execute it, it says load the first local variable or the first argument A that we have passed. It has value 5. Push it on the stack. So this is the stack. Then the next bytecode iconst 1, it says load the constant value 1 on top of the stack. Okay. Then I add, as you would have guessed, it says pop the top two arguments from top of the stack, add them, and store the result again on the stack. So we have 6 on top of the stack. And I return, surprisingly, returns the value. So pops the top value on the stack and returns it. So this is how it gets executed, and all these values, all this I refers to the integer type here. So there are different versions of bytecode for different data types. Cool. So this sounds simple, the interpreter-based approach, but you may know interpreter-based execution is quite slow. So how slow it is? So basically what I did is I took our myIncrement method, put some benchmarking code around it, using Java micro benchmarking harness. The source code is available in the Docker image, so you can run this example. So basically I'm executing this myIncrement method with 3 different types of modes. So first one is with only interpreter. The second one is using only client compiler, and the third one is using the Graal compiler. And here in the score column, you will see the score for that particular mode of execution, and the unit is nanoseconds per operation. So that means these many number of nanoseconds, so 41,000 nanoseconds are required to execute myIncrement method once. So if you just see the numbers, you will see the client compiler is executing about 70 times faster than the interpreted mode of execution. And the server compiler, or the Graal compiler in this case, is about twice fast or 1.5 times faster than the client compiler. So these are the different modes of execution, and this is the performance difference that you would see. We have a very simple example. That's the reason we cannot see the real power of the top tier JIT compiler or the Graal compiler in this case. So you may wonder, okay, the interpreter-based approach is quite simple, stack machine-based execution, fine, but why is it so slow? And if you think about it, we have this myIncrement method, where if you know some assembly, you would expect something like, okay, we are reading the argument, probably one instruction, they're adding one to it, another instruction, and they're returning the value, right? So about 3 instructions we want really to execute on any machine. So if you look at the assembly that is generated or executed for only iload bytecode, so this is the big sequence of assembly. You don't need to read through it, but you can see by just the size of it, it's a big sequence, which is much more than what we want. We were expecting some sort of 3 instructions, right? Like to add a value or add one to the integer argument. So what I did, I measured this, you can see this size, and I added all the sizes for each bytecode. What's the size of code that we are executing? So if you see, with the interpreter, we are executing about 1280 bytes, and for Graal we have the code size of 96 bytes. Certainly the code size is not the perfect metric for measuring the code quality, right? If you have some optimization, it may have larger code, but it would execute faster. But it will give a rough indication like how or what kind of quality of the method or the code that we are getting generated. And all of these versions, they are executing the same method, therefore the same method, like adding one to the argument. So you are executing this big sequence of instructions here to do the same task as you are doing with this 96 bytes. And you can see you can see the code quality is quite low if you go with the interpreter mode, but it has faster startup time. So the assembly sequence that we saw, it is already generated. So basically, interpreter has this big switch statement. You say, oh, I want to execute this bytecode. Go to that case. The assembly is ready. Execute that sequence of assembly. Then go to the next bytecode. So if you do something like add one, subtract one, add one, subtract one, it would just do that. It wouldn't see like, okay, you are not really doing any meaningful computation. So that's the reason you have low startup time compared to the compiled version, where you look at the code, you see what optimizations can we do, then you optimize the code, and then you say like, okay, you are basically doing adding one to it, so this is the sequence that you should execute. So that's the trade-off that you have with different modes of execution. And what JVM does is we cannot execute all the methods with faster startup time, and we cannot execute everything with the top tier JIT compiled approach, because it would take much longer. So JVM makes this trade-off. So depending on how often method is called, it would move from one version to another. So these are the numbers for hotspot JVM, and after 2000 invocations, JVM will submit a request for compilation. It would not directly switch to the the version compiled using client compiler, because that needs to be compiled. So probably it would take a few more invocations, and then it would go to the compiled version from the client compiler. So the same thing would happen. That version will be executed for another until the invocation count reaches 15,000, and then the request will be submitted for compilation using the Graal compiler. Cool. So if you are curious, you may wonder like what assembly you would see if you execute in C, and why C-based execution is faster. So here you can see this my increment method, and here we have our add instruction. So just to know what this add instruction is, so it should be read like W0 is the result of W0 plus 1, because this is add instruction, and this add instruction will make more sense when we will go further, and we will try to see when and where this add instruction gets executed using our using our JVM and in the compiled version of the method. Okay, so this is a quick question for you. So we saw JVM goes from the interpreter to the JIT compiled version, first the client compiler, then the server compiler. And after certain invocations of the same method, it does the JIT compilation. So if you remember our original my increment code where we called our my increment method once, how many JIT compilations do we expect if we execute that program? Please raise your hand for 0, 1, 5, more than 5. Cool. So these are the methods that get, these are the methods that get JIT compiled, even if you execute this my increment method once. There is no my increment. My increment method, you were right. My increment method doesn't get compiled. But these are all the other methods that get JIT compiled, and that's the reason when you execute a simple Java program, then also it takes a bit longer time to run, because there are many other subsystems of JVM, such as class loader, that needs to be ready and ready to load the classes. So you may see many methods here. They are from java.lang.string, because you need to read the class name, which class you want to execute, and doing all sorts of things. So you may also see this object initializations. So that may explain why there is much longer time to execute a simple application in Java. We are not going into the details whether one thing is better or another. So let's see, we are talking about JIT compilation. So how the JIT compilation happens. So you may have heard this term Graal VM in many contexts. For example, ahead of time compilation, compiling different languages on top of JVM in a single code base. But for today's discussion, Graal VM is our hotspot JVM, with Graal as a top tier JIT compiler. Okay, so we have Graal VM, and one interesting part about Graal VM is Graal compiler is written in Java. So as Java developers, you can use your day in day out tools, all your IDEs, all your debuggers, all the tools that you use. You can use the same tools to look into the code base for Graal, debug it. You can play around with it. So on a weekend, if you want to just see how certain thing works, you can just clone the repo and you can start playing around with it. And that was one of the overheads that or the learning curves that I faced when I was looking into the C2 or server compiler. It is written in C++. It has its own learning curve. So, because it is written in Java, the Graal compiler is written in Java, it is essentially a Java program, right? So, it takes some input, which is the bytecodes. JVM gives the bytecodes and say, compile this for me. And then it gives the assembly to JVM, like, hey, I have compiled everything. So, what we expect is something like this, right? Some class called Graal. Then there should be some method compile. It should take bytecodes as input. So it is a byte array, a sequence of bytecodes, and should give the assembly sequence in return. So there are also a bunch of ones and zeros, all the bytes. Cool. So we will try to find whether we see all these things in the Graal's code base. And the idea here is to just give you confidence, like, hey, even if it sounds compiler and a bit scary, it's very easy to dig into it and learn and figure out how something works. So when it goes from bytecodes to assembly instructions, Graal uses the intermediate representation, which is graph-based, which is optimization friendly. So you will see many graph-related things happening there. So that's what we are expecting in Graal. Okay, so because it is a Java program, we can stop it in a debugger. So this is IntelliJ. And I have stopped this program during its execution. So what does it execute? So during its execution, it is compiling a method. So I have stopped it while compiling our myIncrement method. You will see here, we will see a bit closely each part of it. So we have our hotspot Graal compiler. So we were expecting some class called Graal. So you have hotspot Graal compiler there. Then there is a compile method. Okay, so now we want to figure out where is the sequence of bytecodes goes in and how the sequence of assembly comes out. So here we don't have the byte array as a return value. We have compilation result. We will see whether that result has a sequence of assembly. And for input, we have this resolve Java method, and IntelliJ is nicely showing here. This is myTest.myIncrement method. So this is the input argument. And we want to see whether it is passing the bytecodes for our myIncrement method. Okay. We also have this graph here, which is the intermediate representation for, again, myTest.myIncrement method, and we will see whether we can find all the information that we were looking for. So again, this is the method variable. If we expand it, you will see another field called code, and it has 4 bytecodes. It is the byte array with 4 bytecodes in it. And if you remember, the bytecodes for the myIncrement method, we had 4 bytecodes, right? If you are still not convinced, this is the screenshot from Wikipedia for different bytecodes, and this is the hexadecimal value. If you can do hex to decimal in your head quickly, you can find those numbers are same. The negative one is because it is more than 127. The sign bit is set. But anyway, now the compilation result. So we found the input bytecodes in our debugger. Let's see whether the result has the assembly output. So this is the compilation result that the method compile method was returning, and this is the target code, which is again the byte array. So you have your input bytecodes being converted into the graph-based representation. We will look at it closely. So here is your graph-based representation, and you have the assembly output as well. So sequence of bytes. Now the graph-based representation. So this is of type structured graph. Again, it's for our my-increment method, and it has 6 nodes. Start node, parameter 0, constant 1, plus return. We are doing like argument a plus 1. So this sounds kind of similar, relevant to that. But this is not definitely the most friendly way to visualize it because it's a graph, right? So there is a tool, Ideal Graph Visualizer, that you can use to visualize this graph-based representation. These are the identifiers of the nodes. We are not interested in it. So you will see the same nodes over here in the graph, and if you want to read this graph, it should be read like this. So we start from the start node and return the value, the line, the red or orange line connecting it, it's the control flow. So this is how the control moves further. And the blue line is the data flow line. So return will return the result of addition, and addition of parameter 0, which is the first argument, and the constant value 1. And as you know, integer is of size 4 bytes in Java, so it's I32. So it is doing the addition. Cool. So each node has a generate method. So now we want to see how this graph-based representation gets transformed into the assembly. So each node has this generate method. So if you go into the generate method for add node, remember we are looking at add node and we want to find that add instruction. So if you go in there, you will find this gen.emit_add, and if you click on it, if you try to see the implementations, you will find 2 implementations. One is ARC64 arithmetic LIR generator, and the second one is AMD64 arithmetic LIR generator. So until this point, all the graph-based representation that you saw, all the processing and all the optimizations that compiler does, they are platform agnostic. The part from the further steps, they are platform specific. So here you have implementation for this add node for 2 different architectures. So AMD64 is like for Intel and AMD processors, and ARC64 is 64-bit ARM architectures. So let's look into the ARC64's implementation. So if you see, you have this add operator here, and if you look around this method, you will find the alternative versions of the add instruction. So one is floating point add, you can see here, then there is add s. So this is another add instruction, and if you keep digging into it, you will actually go to the opcode and the actual bytes that are emitted, because they would not make much sense, so we wouldn't do that now. But you can keep digging into it using your editor. Cool. And we can extract the assembly for our method from using some JVM flags, and you will see our add instruction here. So this is again W0 equal to W1 plus 1. So here, instead of having W0 here, we are having W1 because there is this pointer being passed as the first argument, the default first argument. So you have your first argument as the second one, but it's underneath in the compiler. And you can figure out all these things in the debugger, which is quite interesting. So let's see how a compiler optimizes a code. And it is useful because this would help you to see like, hey, I have this particular sequence. I wrote this code and I'm not sure whether it would degrade the performance or not. Certainly you can measure the performance, but it may work like it is faster on some hardwares or on some machine, and it's slower on another machine. And if you want to debug that kind of scenario, you may find this particular pieces of code relevant, like, hey, I want to know how the multiple null pointer checks are eliminated, how lock elision happens, for example. So this is a slightly modified version of our myTest.java. So we have the main method. We are calling myIncrement method 1,000,000 times because we want it to be JIT compiled. And remember, as soon as it hits the invocation count, like 2,000, 15,000, it submits a request. But in the meantime, the code is executing. So we want to execute as long as we can so that the compilation happens and the compiled version will be executed. So that's the reason we are calling for 1,000,000 times. Then we have our myIncrement method, which does the same a plus 1, but before that it multiplies the argument by 16. So this is my mult. We are multiplying by 16, adding 1 to it, a pretty complex program, right? So let's see the graph for this program. So if you see here, again we have the start node, return the result. Return value is the addition with constant 1, and before returning the result, we are also adding the multiplication of parameter 0 and multiply by 16. So we do a multiply by 16, add 1 to it, and return the result. Okay. So this is the screenshot from Ideal Graph Visualizer, which allows you to look at how the graph look like at different stages of compilation. So this is the version as soon as you parse the bytecodes and convert them into the graph-based representation. If you see afterwards, at the end of the compilation, it's actually just the end of top tier or the platform agnostic optimizations, it would look something like this. So you see, we had this multiplication node, which got converted into this left shift. And instead of multiplying by 16, we are doing left shift by 4. So on hardwares, typically multiply may take longer than the left shift. So this is the simplification of the multiplication that compiler has done, and you can see it here. So, and here you can see after high tier, mid tier, low tier. So these are the different groups of optimizations that Graal does. And you can see what all optimizations happen during the high tier, mid tier, and low tier. So you may find some familiar name like dead code elimination, inlining, maybe canonicalization, which we will see, and many other optimizations. And for all of them, you have a Java class for it because it is a Java project, and you can get into the code and see how this optimization works. Cool. So getting back to our original example, so we have our code here for my increment, which does the add, and my mult, which was doing multiplication by 16 here. And you may have noticed this is the graph for just my increment method, just the my increment method. And while generating the graph itself, we got the code for my mult as well. So Graal is an aggressive, Graal does aggressive inlining. So it has inlined my mult right over here. So while parsing itself. Cool. So let's see where the multiplication gets converted into the left shift operation. So there are two interesting methods here, canonical and generate. So if we open the multiplication node, so mulnode.java file, you will find this canonical method. It has it has 4 arguments. The first one is stamp, which stores the information about the data types. Second one is the forex, which is the first argument, or in our case, it's the value of a. The second one is constant value I. So it is the 16 that we have because we are multiplying by 16. And we are going to ignore this one. It is not of our interest at the moment. So essentially we have A and value 16 in I. So imagine instead of 16, if we were multiplying by 0. So multiplying by 0 means value is 0, right? So you are returning the constant node with value 0. If you are multiplying with 1, the answer is the same variable, right? A multiplied by 1 is A. So you are returning A here for X value. And this is interesting. You can see the multiplication had multiplication value A and then 16 or some other value here. But here if we multiply with 1, instead of having these 3 nodes, we will return only one node here, which is only value A. And this is how, if the node is not present in the graph itself, we wouldn't have instruction in the output. And that is how this simplification happens. So you can understand how a particular optimization will impact or influence the quality of the output and what happens exactly. So going further, multiply by -1 is the negate node. We don't need to do the actual multiplication. And this is of our interest. So we were multiplying by a value which is greater than 0, and it is a power of 2. If it is a power of 2, we left shift. Instead of doing the multiplication, we do the left shift for A and value 4. So we need to compute what is the value to be left shifted with if we want to multiply by 16. So this is 4. If we look at the assembly, we will see this OR instruction, which is essentially doing W0 equal to 1. Then we have this add instruction here, which is doing W0, W0, W1, and this left shift by 4, which means W0 plus W1, which is A left shift by 4, which is A multiplied by 4, and plus 1. And W0 holds the return value. So this is how you can see how our source code got converted into the assembly. Okay, now you may wonder, we saw like, okay, we had the mul node which got replaced with the left shift node, and we also had another node which was the add node. So we should have seen two instructions, one to left shift and one to do the addition, right? Because one node gets converted into the assembly, which is one instruction. So we should have seen two instructions. We have only one instruction, which is doing both the operations. So there is a part of compiler. Many compilers use these kind of match rules. So the idea is you look at the graph and you try to find a pattern for which in your hardware you have a special instruction. So for ARC64, like many other platforms, you have an add instruction which can do addition as well as left shift at the same time. So instead of 2, you can emit only one instruction, and that basically results in better code quality, right? We were looking at why with interpreter you have so many lines of instructions, and why a top tier JIT compiler can emit a better sequence of assembly. So here we are not going to look into it in detail, but if you want to see, because it is Java again, it's an annotation. So you write a match rule like this, where you say if you have an add node with X and another operand as a left shift by constant. So this kind of pattern, if you find, we have got an instruction for you. And if you see closely, this is ARC64 node match rules. So here we are going from platform agnostic to platform specific part, and we are doing optimizations for platform specific bits. So if you have special instructions, so you may find in java.lang.math, if you may have functions like FMA, absolute, and there are instructions for that, then here is the place where you will find those patterns in the graph, and you will emit special instructions for them. By the way, there is a special instruction that that sets the value 0 for JavaScript, something like that, which is quite interesting. So, and these match rules are written in Lisp a style domain specific language, so you will find more about it in the documentation, but it is quite interesting. So you can know how a particular sequence got optimized all the way from source code to assembly, and you can dig into a certain aspect of your interest as much as you want. Um, okay, so to conclude, we looked at Graal as a JIT compiler. So you can use Graal as a top tier JIT compiler in a hotspot VM. You also saw a graph-based representation of a Java program. You saw certain optimizations that some were platform-specific, some were platform-agnostic. So platform-agnostic was the one where we simplified left shift, multiply with the left shift, and the platform specific one was emitting a special instruction to do both addition and the left shift in the same instruction. And we also see how we go from the graph-based representation to assembly. Things that we haven't seen, and therefore they are quite big topics in themselves, such as instruction scheduling, register allocation, Graal intrinsics. So this is the part which I was working recently. So this is something like you say in the graph-based representation, if you have a particular method, let's say string.indexOf. So you say, okay, this is the method. Don't do anything during the optimization phases to this particular node. Let me handle it. And at the end, you emit a sequence of assembly instructions for that. So these are the Graal intrinsics. Graal native image, you may know, you can compile your Java program ahead of time and you can execute it. Graal to run other languages, so you can run polyglot programs using Graal. So we haven't seen that. And there are other JVM components that we haven't seen, such as garbage collectors, which are big topic, which are big area of research as well, class loaders and components like that. So I hope you got enough info to at least poke around the code base and how compilation happens roughly. So thank you for attending my talk. If you have any questions, please feel free to ask. These are some of the resources, and all these slides and everything should be available on GitHub. So thank you. Oh, yes.
Just a question. You said that a compilation just in time is, I mean, you need to be fast. So does Graal JIT itself so that it can be faster
Yes.
at runtime?
Yes. So when you start executing, there are certain parts of the compiler themselves get compiled. So that also happens. Then there is also an approach where you use ahead of time compiled Graal to compile other stuff. So you attach it as a library. So you will find more information about that on 10 things to do with Graal VM, this URL. It's quite interesting. Any other questions? Yeah.
Hi, yeah. What about debugging? How on earth do you start debugging?
Oh, that's a good question. So it's, well, sometimes when you emit a particular sequence and it's seg faults, so you don't see seg faults in JVM, so we see that quite a lot. So what you do is you make the program to execute a particular sequence where it fails, and then you attach a debugger to it. So what I don't know whether this is a well established approach, but what I do is I put a breakpoint. So okay, so what I do is I make it emit the assembly, for a particular method which is causing a problem, and I'm trying to emit a better sequence for it. So I asked JVM to dump the assembly, and the function that dumps the assembly, we put a breakpoint there. So in the JVM's code itself, so you use GDB to debug the JVM, and then you put a breakpoint in the function that dumps the assembly, but you haven't invoked that code, because if you invoke that code, everything faults, right? It stops. So then you stop it and you make the entire VM to pause, and then you go line by line and see all the registers, what values are there, and sometimes you realize that you made some mistake here, you're not emitting right instructions, you calculate hex addresses, and yeah.
Okay, so basically you're single stepping through the assembly.
Yes, yes. It's fun when it works.
Hi, thank you. This was an extremely enlightening and enlightening talk. In more complicated examples where you have a method that calls another method that calls another method, and it goes on and so forth, I'm guessing there has to be, it's not all compiled all the time. There has to be interactions where it gets back to just executing interpreted bytecode. Does that contain any performance implications? I mean, is it significantly slower?
If a method calls a method, and like that sequence, that happens all the time in the application, right? And we want to especially compile those. So debugging those compilations would be a challenge, but we want to compile those methods. So yes, that happens. And especially Graal is a really aggressive. Graal does really aggressive inlining, so it will try to inline many method calls into one, and you will see the assembly. So for example, we haven't looked into it much, but if you look at the assembly, you will also find here which line of code. So it is saying my JIT demo dot my increment at 7, and it is from line 10 of the code. So at 7 is the 7th byte code, if I remember correctly, and line 10 is the 10th line in the source code. So you can see exactly how the method is compiled. But if you are working on a particular performance problem, then what we do is we look at the code, you simplify it, and make sure like you use profiling and see, okay, it's taking more time here in doing hash maps, and then you take that hash map kind of example and you write a synthetic benchmark or some example where you will stress the hash map, like putting million values, and see where it takes more time. So you kind of extract that piece of code and put it in the benchmarking setup to really see what's happening there. So I think some questions.
Going back to the segfault handler, does Graal also do the optimizations? Like in the case where it detects that in practice this value is never null, so it just skips the null check?
Oh yes, it does a lot more optimizations, and many optimization passes that you had seen. You can find information, you can get into that what exactly happens. So definitely, like if you have an object and you have checked it is not null, and in a sequence of code it is not checking, you don't want to check whether it's null all the time. So what happens is typically all those null checks will float in the graph-based representation, and you see like, oh, I have already done that, it hasn't changed. And instead of doing that all the time, you do it only at once at the beginning until the variable's value is changed. And you can see all that happening, like where it eliminates the null checks in the graph-based representation. And rather, I've shown a very simple example here, but for a big piece of code, it will work exactly in the same way. Rather, well, when you are debugging some compilation, you don't want to see really big code because the graph will look enormous. But then the same approach JVM takes to execute your method. So yeah, it does speculate a lot. It says like it will, and the thing that we haven't looked at is de-optimization. So when you're compiling, it will assume that in the if-else statement or the exception handling, it will assume like exception will never occur. It would not emit code for exception. It will just have a trap. So if that happens, then You just go to the interpreter mode again, go through the same stages, you do C1 compilation, then Graal compiler, but this time you don't speculate that error would never occur or this value would never be null. But then when you compile for the first time, it will definitely speculate.
Hi. So we saw Graal is doing compiling, optimized compiling inside JVM. Then why it's called Graal VM instead of Graal compiler?
Right. So that's probably, initially it was a Graal compiler. It was part of the Maxine VM project, the JVM. And then that compiler, so there was development from Oracle, then different aspects got into it, such as executing with different languages on top of JVM using the Truffle framework. And the Graal VM term got polymorphic over time with all the branding and probably marketing stuff. So,
Okay, so in reality, it's not a virtual machine. It's actually a compiler.
so Graal VM is the hotspot JVM with Graal as a JIT compiler.
Okay, okay. Thank you.
That is a question.
Just coming back to what you said about the exception not being optimized in Graal, is that the reason why people say exceptions are, you shouldn't use exception for control flow, you should not, because it's because they're not optimized?
So compiler will try to optimize even exceptions. So first time when you are compiling a method, it will kind of wouldn't emit all the exception handling code. So compiler will take care of that. But when the exception happens for the first time, your code gets de-optimized, goes back to the interpreted mode of execution, gets recompiled, but this time it goes and it will emit the code for exception handling as well. So it will have a faster version of exception handling in the code. So it depends. It may have some performance implication if you have a lot more exception handling naturally, but it shouldn't make much difference, I think.
Okay, thanks.
Okay, so thanks everyone.